Here's Ben Steiner. Ben and I used to work for the same firm a while back, although never crossed paths, and we've done some work recently. And so I invited Ben to, you're probably seeing Ben, he does lots of presentation, lots of different places, and he's currently a lecturer at Columbia. So Ben, take it away.
Thank you, Patrick. Thank you for the invite. Hopefully
Sure.
you can hear me okay. Hopefully you can see my
everything is
screen okay.
fine. I could see your
Excellent.
screen. I could see.
So hello to everyone. It's good to be here with you. This topic is going to be about managing the risk of using deep learning strategies or techniques to create investment or trading strategies. Lots of buzzwords there. So let me give like a high level overview before diving in. Model risk management. Look, any model involves risk, and we need to manage the risk of the model itself. Investment strategies, quite simply, are systematic rules for buying or selling assets. And deep learning, well, if I was doing this in person, I'd ask for a show of hands. I'm guessing everyone by now has heard of deep learning. It's one of the big buzzwords. It's been doing the rounds for the last few years. And that's where this presentation started. Because about 4 years ago, I was very curious, based on all the deep learning that everyone was talking about, how it could be used in finance, and specifically what the application would be for the types of investment strategies that I was working with. Now, this presentation grew out of that, and what I'm going to show is various things that came out of that research. My career has been with various hedge funds and investment managers, originally as a quant researcher, then as a quant portfolio manager, head of model development team. Most recently, I was in the global fixed income investment division at BNP Paribas Asset Management. And as Patrick mentioned, I teach an applied modeling course at Columbia. So what are we going to talk about? Well, here's the agenda. I'm going to start with a few introductory concepts around model risk management and machine learning. Then I'll describe 3 challenges of using deep learning for investment strategies, both real and perceived. One of them is very real. 2 of the others are less so. And then what I really want to do is get to about 10 minutes at the end, where I'll describe examples of model risk management for investment strategies and show some examples. So let's get started. Look, any model, as we all know, is just a simplification of the real world. The model is not the real world. So there's a difference between the model and the real world. And model risk is that difference is too big. Where does model risk come from? Well, it's using a bad model. Now, a model can be bad because it's wrong, in inverted commas. It's a fundamental error. Or a model can be bad because it's used inappropriately. It's misapplied. It's not fit for the purpose it's being used for. So model risk management is intended to minimize the consequences when we're using a bad model. There's 3 elements, if you like, of model risk management. Different organizations have different names for these, but the way I think about them, there's the conceptual soundness stage, which is, are we doing something that we believe to be correct? Does the strategy make sense? Is theory being applied correctly in the correct way? Then there's the implementation validation piece, which is, have we actually implemented and coded up what we wanted to? Have we minimized, ideally avoided, any coding errors or coding bugs? And then the final part is ongoing monitoring, which is once we put a trading strategy into production, monitoring it continuously. Now, the second one of those 3, the implementation piece, that's addressed with things like elevation and release cycles and version control and continuous integration, automated testing, and so the IT productionization. I'm not going to touch on those in this presentation. The risks I am going to talk about today are related firstly to the choice of the investment strategy. When do you turn something on? How do we evaluate strategies to decide which ones to use? And then the third part, which is the ongoing monitoring, which is basically, when do we know when to turn a strategy off or to take risk away? I'm just going to update my screen so I can see myself if I can. Okay. So George Box, as you might realize, this funny accent isn't from New Jersey or New York or the tri-state area. He's an Englishman. I'm an Englishman. George Box said all models are wrong, but some are useful. I've misinterpreted what he said to basically say this was all about model risk management. And model risk management is all about understanding and controlling how wrong our model might be and the consequences if a model is wrong. Definitions. Machine learning has 101 definitions. I like this one. It's short, it's snappy. Using algorithms to learn from data without relying on rules-based programming. When I was in high school, sounds a bit like statistics, a bit more of that shortly. And then deep learning maps the inputs to the outputs using multiple layers of nonlinear processing units. For those of you that understand deep learning, it'll make perfect sense. For those of you that don't worry, I'll show a visual example in a moment. It basically means that there's layers that use the output from the previous layer as an input. I'll show an example shortly. Before that, I just wanted to show a quick ontology of the different maps of machine learning. It's not exhaustive, but it gives examples and it puts deep learning in the right place. In blue, we've got the supervised learning, which is learning from data sets with labeled output. In red, we've got the unsupervised learning. When there's no label, instead the learning involves classifying or clustering into similar groups. And then in green, we've got the reinforcement learning, which is techniques that learn from trial and error. Now note that linear regression and logistic regression are in the supervised learning area. When I was in high school, we called those statistics. They've now called, I think, classical machine learning in the rebranding. But the key point is that deep learning are the neural networks. Deep learning are the neural networks that have been around since the 1970s. We've just got an extraordinary amount of computational power in the last 50 years. But the theory, certainly has its roots in the 1970s. An important question to ask if I'm making a statement that it's all about model risk is deep learning and machine learning in general, is it really still a model? Some people might say no, but I would very vehemently say yes. Machine learning is still a model. It's still an approximation of the real world. It just grew up from a different culture to traditional statistical models. Now, don't take my word for it. People who are much smarter and much more well-established than me have said the same thing. For example, Leo Breiman, Professor Breiman, he's a well-known statistician who was at UC Berkeley. He wrote a paper 20 years ago, back in 2001, on the two different cultures, sort of the culture of statistical modeling and the culture of machine learning. And it's a nice, snappy paper. It's called Statistical Modeling, the Two Cultures. This cartoon hopefully summarizes what is a very short paper. For those of you that haven't read it, I'd recommend reading it. But the key gist of the paper is that on the left-hand side over here, we've got this guy, the data modeler, as Breiman called him. And the data modeler was the traditional statistician. And he's saying, assume the data are generated by ... He'll make assumptions about the structure of the equations. He'll make assumptions about the variable distributions. And then once that's done, he'll select candidate variables, he'll do his variable transformation, he'll calibrate his model. But it all starts with him making some assumptions. Now, contrast that with the guy on the right-hand side, who Breiman called the algorithmic modeler, but we would now call him the machine learning computer scientist. He just wants to use data. And he's saying, I don't want to assume anything about data, just make me some predictions. He just wants now, I don't know if it's coincidental, but the left-hand guy looks like a fuzzy-haired professor in the statistics department. The right-hand guy's got sort of the slicked back hair. Maybe he's like the VC Silicon Valley startup guy. I don't know, that might be coincidental. But the key point is, for me, that machine learning is just a set of tools. It uses data, it uses statistical techniques. And key point two is we're still just finding relationships between inputs on the one side, or the independent variables for the traditional statisticians, and the outputs on the other side, or the dependent variables for the statisticians. Deep learning, like any machine learning, like any model, has a certain level of accuracy. It has an error rate, it has a failure rate, it has an error term. It's still a model, and it can still be wrong. So we still need model risk management. Just as actually as an aside, Breiman also came up with classification and regression trees and random forests as an ensemble technique. So he kind of knows what he's talking about. Okay, let's do a quick sort of deep learning 101. I'm not going to go into the details. Those of you that have studied this will know this already. Those of you that haven't, it's just more just a picture, a visual picture. We have an input layer of data we're pouring into the network. We have an output layer of the things we're trying to predict. And then in between, we have these hidden layers. And the key point is that every node is a weighted transformation of every node in a previous layer. So this little guy up here, this Y1, is a weighted combination of all the inputs with a certain set of weights with some transformation. And the transformation is traditionally nonlinear, rectilinear, or some kind of tan H function. So the key point is to end up with our predictions on the right-hand side, we have to evaluate what these weights are going to be. And there's an iterative technique known as stochastic gradient back propagation, that entails going backwards and forwards through the network from left to right. We go from left to right making guesses, and then we go from right to left improving our guesses, and then we go left to right, right to left, left to right, and we end up with a decent probability. Can you still hear me okay? I'm getting a warning that I've got low system resources.
No, I could hear you very well, fine, Ben.
Perfect. So that's the picture in 30 seconds of deep learning. Obviously, deep learning is much more complicated. Obviously, this is just a very simple, plain vanilla left to right network. There's all sorts of architectures that now get used. But let's jump in to the challenges. So let's move on to the challenges of deep learning. Now, the challenges of deep learning for financial markets come from the nature of financial markets themselves at certain timescales. What we really want to understand, we know financial markets change, and that goes without saying. What we really want to understand is how quickly the markets change relative to how much data we need to learn that the market's changed. So we don't want to be continually chasing our tail. We want to be learning and updating and have enough data to relearn. Otherwise, we just are continually chasing our tail. But in order to explain that in a bit more detail, let's think about other domains where deep learning has seen success. So for example, autonomous vehicles, UAVs, cars on the roads, and so on. Well, these use forces of nature, and we can collect data experimentally or by simulation by either sending cars out onto the road or creating computer simulations to learn about and understand the forces of nature. And those forces of nature don't change. So gravity, friction, acceleration, trees being a solid surface if a car bumps into them. You know, a tree is solid tomorrow, yesterday, and next month. Gravity doesn't change. If we move from the physical world to the virtual world, and we think about where deep learning is being used originally for game playing, if you think DeepMind in London, Atari and Go and protein mapping and so on. So here, not only are we collecting data experimentally, but we can do it critically in faster than real time. So we can have a computer simulation that has 1 CPU or 10 CPUs or 10,000 CPUs. So literally overnight, we can speed up the learning rate by just throwing more computing power at it. Not only that, we have this unlimited opportunity for trial and error experience. Unlike crashing cars into trees in the physical world, you write off the car. When we're playing video games or doing a computer simulation, there's basically zero cost apart from the cost of the simulation environment. And then the final thing about video and simulations is that the rules of the video games are fixed. We learn the optimal behavior from rules that can't and don't change. So the experience that gets learned never actually expires. It's always relevant. Of course, financial markets are different. Yes, we can collect data, but the factors that are driving prices up and down do change. So we have what's called restricted trial and error experience. At some point, our data that we've used for training becomes obsolete, and it does not represent the future. The world is changing. So we really want 3 things for deep learning. First of all, we want to collect data in faster than real time. In trading and investing, can we collect data in faster than real time? Some people are doing a lot of work on simulated data. I know Shri spoke about that earlier. My personal view is that if you have a good enough model to give you a good enough simulation of the return of an asset, you don't need deep learning. You can just use your model, and then that's not synthetic data, it's a real model. So I think for investing, we actually use real data. That's the point. We also want an unlimited opportunity for trial and error. Now, in investing, error or failure comes at a cost, i.e. trading losses. So we don't have a unlimited experience for trial and error. And finally, for deep learning, we want our learned experience to be constant or only change very slowly and predictably. In investing, is that the case? Sometimes yes, but sometimes no. So the question I'm really excited about answering and working with people on is the ratio between how much data we can collect and how often the driving factors change and how they change. So I'm going to talk about non-stationarity as the first challenge. And there's two other then challenges that I'm going to mention now, but then skip through for reasons of time. One is interpretation, and the other one is learning what we already know, or ensuring we're only learning that. I'm not going to spend time on them because I actually want to get to the third section, but there are those other two challenges out there. Emmanuel Derman is a professor at Columbia, and he had this great quote that I love over 25 years ago. A model may be reasonable, but the world itself may be unstable. What's a good model today may be inappropriate tomorrow. That was over 25 years ago, and it's buried in the footnote of a Goldman Sachs research paper. So model risk management is nothing new. And recall that one of the elements that's a key tenet of model risk management is a model no longer being fit for purpose because the world around it has changed. So let's talk about this idea of the world changing. Here's 3 time series on the right-hand side. It shows individual observations with time on the x-axis and sort of return on the y-axis, and say there's 3 assets. In the top chart, the top asset has a constant mean, approximately. The middle chart sort of has this sort of regime shift at some point, we believe. And then the bottom chart has this sort of step function that goes up and down. Now, maybe I can ask you all to type into the chat box, which one of these do you think is stationary? Let's make this interactive. I think I've got a bit of time, I hope. Is the top one, if you think the top one is stationary, type 1. If you think the middle one is stationary, type 2. If you think the bottom one is stationary, type 3. If you think more than one are, type a few numbers. Let's see what the numbers are.
1 so far.
I see a 1. Thank you very much, Eric, for being brave.
1, 3, 3,
1, 3,
1, 3, 3. Oh boy.
Thank you all. Thank you all for playing the game. This is just to prove to me that people are awake. So thank you. If someone thinks 3. So let me sort of put you out of your misery, because
The answer is
the middle one is the first part of the middle one is the top one, and the first part of the bottom one is the middle one. So basically, these are all the same asset viewed at different time horizons. You know, one is zoomed in, one is zoomed out. So the description of stationary or non-stationary, this asset is the same, but it's the way we're viewing it that would make it stationary or non-stationary. And that's an assumption of the modeler. And whether it's stationary enough comes down to our time horizon. But the key message is it's not the nature of the asset itself. It's sort of the decision of the modeler. So I could show 2 modelers the same data, and one modeler might choose to build a stationary stochastic process, and the other modeler might choose to build a non-stationary deterministic model with regime shifts in it. And they might both have decent models, but the decisions they made early on about stationarity or non-stationarity influence the modeling process they go down. So the key point here is that change, or this sort of stationary idea, is in the time frame of the beholder. If I'm a 30-year pension fund, I might have one interpretation. If I'm a high-frequency trader, I might have a different one. Now, the issue of trying to model a system as it changes comes up in many different domains. In machine learning and data mining and predictive analytics, it's called concept drift. In pattern recognition, it's called covariate shift or data set shift. It's basically, what I like the idea of concept drift, and I'm going to talk about concept drift. That's the one term I'll use. When the statistical property, what is concept drift? Well, when the statistical properties of the target variable that the model is trying to predict change over time in unforeseen ways. Now, note the definition of unforeseen. So the thing we're trying to model changes. I've got a 10-year-old son who plays soccer, football to me, because I'm English, and football is a game with a round ball and you play it with your feet, so we call it football. You guys over here call it a different game, but there we go. He plays soccer. And the target variable or concept drift to him is, imagine him running down the field, he shoots at the goal, and suddenly the goalpost moves and it jumps to the right, or it moves behind him. The goalposts moving is concept drift. And that's basically financial markets. The things that drive markets can change. It's the unforeseen substitution of one target variable with another. Now note, if we could predict how things are going to change, classical time series analysis with drift or trend and moving averages, that's not concept drift, because we can deal with those. Yeah, those are predictable and dealable. If that's what a time series is doing, if a time series is a sinusoidal wave with drift, it's not a financial market. So that's not concept drift. Concept drift is things where there's changes in unexpected ways. So how do things change in unexpected ways? Well, in lots of ways. Imagine there's two states of the world. There's state one that's driven by the features in our data, and there's state two where the market is driven by features that are unknown to our model. So this is the real world changing. The question is, how does the market change from state one to state two? Maybe it makes a sudden shift. Maybe it changes incrementally. Maybe it bounces backwards and forwards. Maybe it goes up for long enough that we can relearn the new market. Maybe it just bounces in between, or maybe it's noise. So this idea of concept drift can come in many shapes and flavors. And understanding that these are not exhaustive, these are just illustrations. But concept drift is a fundamental idea for when we want to use deep learning. Because if it's happening like this one, it becomes difficult. Now, of course, in the real world, things don't happen so simply as that. Remember, one of the sources of model risk, an incorrectly applied model. If the world has changed around us and we're trading a model trained on the old world, we're losing money. And to emphasize, I'm not really talking about a single time series here. We're talking about the interrelationship of a multiple dimensional system and how all the interrelated variables and assets and drivers affect each other. And we know these change over time. The correlation structure between asset returns changes over time. The data available to market participants changes over time. Think of all the alternative data that's now available. Think of all the decentralized finance, the cryptocurrencies and the alternative data that's influencing them now. They didn't exist 10 years ago. But critically, the relative importance that market participants attach to each of those data sets changes as well. So data just being available doesn't matter. It's when market participants attach weight to that data and make trading decisions based on it. Now, why is this important? Well, if we understand when and how concept drift is expected to occur, i.e. in which markets, over which timescales, that can help us understand when deep learning should and should not be used. So the big questions are, how much data is enough? And that depends on the algorithm we're using and the system we're working with. And then how can expected change in markets be measured? Now, we can't predict concept drift, but it's a bit like earthquakes, that you might know they're more likely to occur in long-term versus short-term, or this asset versus that asset. So when the ratio of volume that we have is high relative to concept drift, crack on, use deep learning. There's tens of thousands of pictures of cats on the internet, and the nature of a cat does not change. Cats don't suddenly have 2 heads and 6 tails. A cat has no concept drift. Use deep learning. But when the ratio is low, i.e. we have limited data and concept drift is high, then deep learning is less useful. So that's the first challenge, the challenge of a world that moves. The other two challenges were interpretation. We need to have interpretation, but since I've got 6 minutes left, I'm going to jump through to the last section that I wanted to talk about, which is how to do model risk management in the last 6 minutes. So in the introduction, I spoke about conceptual soundness being when we turn an investment strategy on, and ongoing monitoring when we turn it off. The good news is we can make back tests. The bad news is we all keep making back tests till the cows come home. So the road to hedge fund failure is littered with good back tests. Unlike the other famous quote, which was said by a famous person, this one was said to me by a potential investor as I was showing him a back test. So that's not to say that back tests are completely useless, but don't look at the performance. Or if you are looking at the performance, don't believe it, divide it by 2. But there's so much other analysis in the back test that is useful. Return per unit risk, alpha decay, temporal P&L, strategy correlation, sensitivity, and so on. So I'll show a few of those now in the next few minutes. So alpha decay is basically, if I delay my strategy by a time unit, so x-axis here shows my time, y shows my risk-adjusted return, say information ratio or Sharpe ratio. How does my strategy performance decay over time? I want to see the top. I don't want to see the bottom. I don't want to see the second one, because that means I have to implement immediately. And if there's transaction costs or there's slippage, I'm going to get killed. Temporal P&L is basically how does my backtest make money over time? These three strategies here all have the same long-run risk-adjusted return. They just happen in different order. Some of them happen at the beginning, some of them happen in the middle, and some of them sort of do better at the end. Now, obviously, I want to avoid secular decay, and I want to trend follow performance. So I don't really want to implement the top strategy, because that could be a situation where there was a sudden concept drift. What I really want is the lower one, where the strategy is getting better and better and better over time. And this is linked back to the earlier idea about concept drift, that there's change in the world of financial markets. Then there's what history can tell us. We want to know when our strategy has done well in the past, but more importantly, in what environments can it be expected to perform poorly? So we can plot the strategy P&L against macro variables or exogenous variables. Now, these three strategies here do better or worse at different times. It's useful information to know in what environments they do poorly. But it's even more important to know what history can't tell us. So we build a backtest, and the backtest can give us the thresholds when we should be trading a strategy. And if the world moves out of those thresholds, be very careful about using that strategy. So if we've got a backtest and we just don't know what's going to happen when the world goes down here, well, that's useful information. And that's when we should turn the risk down, or at least pay attention to that strategy. When we don't know, when we have a backtest that looks good, but it has an environmental variable the world moves into that we've never seen historically. Then there's random portfolios. I could give an hour lecture on random portfolios. Basically, random portfolios are probably the best friend a quant has, which is to try and prove that they're better than a monkey playing darts. Without looking at random portfolios, you might think that this white line here is looking very good, but actually it's doing no better than long run exposure to the asset class. This one down here in the bottom right, I've seen often, which is where someone comes to me and says, hey, look how good my strategy is compared to my random portfolios. And my response is, that's impossible. You've done something probably incorrect. Go back and check your strategy. What we want to see is a strategy that does well, but may not be the best compared to all portfolios. And then we can do random returns. We can break the linkage and the correlation structures between our training data and our target variable, and we can rerun our deep learning. And the deep learning should fail to learn anything, because if we're training it on noise, there's nothing to learn. So if we don't see this picture and we've trained it on noise, we've got a problem. So again, go back and check your work. So that's all about how to sort of review strategies made with deep learning. The last slide is on ongoing monitoring. So we looked at evaluating strategies before turning them on. Now we're talking about how do we know when the world has changed? Recall the Derman quote of the world being unstable, or the idea of concept drift, or model risk management about the model not being fit for purpose. We want to monitor when our strategies are old versus the new world. And this is all about understanding how bad is bad. How bad does performance have to be before we turn things off? But ideally, we don't want to lose a lot of money before turning the strategy off, because then it's too late. So we want to compare the distributions between simulation and live, either time period by time period or trade by trade. The problem with that is we need a substantial amount of live performance, and we've probably lost too much money by the time that happens. So we start doing what was once called statistical process control, SPC, and the benefit of that is that we can work with small samples. This is the opposite of big data. This is the opposite of AI. This is industrial economics from the 1960s. It's basically saying if you expect a 3 standard deviation very infrequently, but you suddenly see 3 standard deviation events 3 times in a row, the probability of that was so small, you probably want to turn your model off because something's changed. So it's about working with small samples, and it's also about testing and comparing the theoretical assumptions of the backtest to the actual realized experience. So things like slippage or locating shorts or your fill rates, to see that if the assumptions of the backtest are in line with the real world. And if they're not, then turn the model off. So to wrap up, I think in the last 30 seconds, if I've done this on time.
Yes, you did.
Model risk management is about managing the risk of a bad model. Machine learning is still a model. Deep learning is still a model. Anyone that's pretending that AI is not a model in finance needs their head examined. We're making approximations and we're trying to learn. So it's about, it's still modeling and model risk. Deep learning can detect or train or overfit any nonlinear relationship between inputs and outputs in the training data. But, out of sample is different to the training data. There's a number of challenges. Financial markets are very different to other areas where deep learning is having huge success. In a stable world, deep learning is amazing. In a world that changes, the key to deep learning being useful is understanding how fast the market is changing and how much data we actually need. I actually want a PhD student, or maybe Patrick, one of your projects, to work on this ratio about the volume of data needed versus the volume of data we've got versus how much a market can change. I think that's a huge area that's ripe for exploitation.
Wait, you can't leave me like this. I'm going to hit you back and you have to go into more detail on that one. Let's talk about that project. Definitely. Wow. Okay.
So I'll just wrap this all up. Last slide. There's lots of analysis we can do around backtests, backtest evaluation to turn strategies on, and ongoing monitoring when to turn them off. But finally, just a word of warning. Just because we can use fancy new techniques like deep learning to build alpha strategies and investment, it doesn't mean we should. If anything, the biggest issue with deep learning is that now it is way too easy. Anyone can do it. Open source technology, cloud computing, processing power has gone through the roof, huge amounts of data. It's now even easier to build backtests and try and raise capital. So my final comment is model risk management can help make sure the code to strategy failure is not littered with deep learning backtests. And that's it. Hopefully I've come in on time.
Okay. Interesting as usual.